Hello, everyone. Welcome. This is Christine Perret. I am happy to chair today's research committee webinar on behalf of the area. It's October 21st, 2020, and this webinar is on the topic of the European Union ARtwin project. So today attendees are in listen-only mode. However, we do invite you to ask questions using the question console of your GoToWebinar application. We have an exciting program here today. We have 3 speakers from the ARtwin project who will be presenting. But first, I'll take a few minutes to introduce the AR for Enterprise Alliance and explain to you why we are here. So the mission of the area is to accelerate the adoption of enterprise augmented reality. We do that by supporting and doing all the necessary functions for a healthy ecosystem to operate. I just like to say that at the top of this pyramid or the ecosystem are the enterprises, the companies who will deploy augmented reality in order to improve performance, productivity, and reduce risk in their activities globally. And of course, those enterprises are beginning to deploy AR in different scales and different use cases. They are being supported by 2 other components of the ecosystem: the providers of software, hardware, services that the commercial solutions that enterprises purchase, and then also the non-commercial entities that are sometimes in collaboration with the software and hardware providers, and sometimes are directly in partnership with their customers. But in general, the non-commercial entities are those that are really doing basic research, many times applied research, and pushing the boundaries of AR technology. The way that the area has been working to support this ecosystem is through these 4 pillars. The first one is to provide vendor neutral and very current, very narrowly targeted content. We call that our thought leadership pillar. We provide content in the form of a very, very deep website. We, of course, have webinars like this. We also have podcasts and blogs and newsletters. And they are to share with people and to inform the industry about AR, about enterprise AR. We also facilitate collaboration and support a community to develop where people can share their experiences and potentially find partners and learn how to really practice AR in the enterprise. There is a skills gap in our industry. There aren't enough people who know how to deploy enterprise augmented reality or to build the solutions that will be deployed. And so the area supports education programs to close that skills gap. And finally, we address the barriers to adoption through committees and interest groups of our members. We currently have security committees, safety committees, and others, and I chair the research committee, which is bringing you this webinar today. The research committee is doing bespoke research on behalf of our members. Our members decide what the research projects will be about, and then we deliver those results. So with those as my opening statements, I'm happy to introduce and to welcome to today's webinar Jerome Royan from BCOM and his collaborators in the European Union project, who you'll be hearing from in a few minutes. So Jerome, I'm going to make you presenter, and thank you very much for your presentation. and contributions.
Thank you, Christine. I hope you can see now my screen. Is that
yes,
okay?
we can. Yes,
okay.
Your microphone is a little hot. You're a little loud. If you want to back off a bit, that would be fine. Thank you.
I hope it's better now. Okay.
It's perfect.
Thank you. So let me present myself. My name is Jerome Royan. I'm working for a research institute in France called BICOM, and I am the technical leader on the ARtwin project. So today we will present you the ARtwin project, what are the main objectives, what we plan to do in this project, and what is the purpose, and we will also show you typically some use cases addressed by this project. So first of all, this project is related to air cloud technology and digital twins for industry and construction 4.0. It's a project that is funded by the European Commission through the ASH 2020 program. The project started last year on the 1st October of 2019 for 3 years. So we are just at the first year of the project, just at the beginning. So what we will present is mainly the plans, but also first results. And the contribution of European Commission is around a little bit less than 4 million euros on the 3 years. And the targeted user for this project are mainly industrial and construction companies, and of course their personnel, and also companies operating in the AR, VR market, so typically the technology providers. So the main goal is to provide a sovereign European air cloud platform for industry and construction 4.0. The idea is typically to move on the cloud some computation that is generally done on request by AR technology. And of course, we will enter in more detail in the next slides. So we can imagine that we have, as you can see on the right figure, some workers on the construction site or on the factory that are wearing some AR devices, AR glasses with camera, but you can imagine also to have camera embedded in drones or other kind of camera, security camera or control camera in the factory. And the idea is to upload all these images on the cloud and to do most of the computation requests by AR solution on the cloud. So here we are thinking about localizing the device, but also creating a map of the environment and put it on the cloud and share it among all users. Why? Because this map will be of real interest to localize the user and to localize the augmented reality device of the user at a very large scale in the factory or on the construction site. But also this map will be very useful to update the digital twin, or more precisely the 3D CAD model embedded in the digital twin. So the idea is to of course implement 3 pilot use cases to test and to validate typically the technology and the platform in of course real environments in factories on construction sites. And one point also is to contribute to standardization. As we know, standardization is a key aspect if we want to reach a real adoption of this kind of technology and to be able to swap, for example, one technology by another one. Standardization is crucial, and we will contribute to API definition in standardization bodies. So concerning the consortium, we have QPlan, that is the coordinator of the project. We have the University of Prague, CTU, an academic partner that is mainly working on computer vision aspect and algorithm on pipelines. Siemens is providing, of course, the use cases, and will provide also the test bed to test typically the platform in a real factory. Hololight is a SME from Germany that is developing a technology for remote rendering for AR devices. Nokia contributes to the project as a cloud solution provider and as a 5G connectivity provider. Artefacto is a French SME, mainly working on AR for construction sites, and will provide the test bed with one of his partners called FH to test typically our platform on a real construction site. And Become finally is lead the technical part and will contribute both on the 5G connectivity, on the cloud platform, on computer vision aspect. So here is the overall concept. As mentioned just previously, we have camera everywhere in the factory and mainly embedded in augmented reality devices. And this camera will create a map of the world because, and I will show that just as a reminder after that, when you are experiencing AR application, what the AR device is doing is that it is creating a 3D map of the world just to provide a good localization of the device according to the real environment. So as a map is created on the different device or can be moved, typically this mapping can be moved on the edge cloud. Each map of the different camera will be able to update a global map of the factory or of the construction site. And this global map in the center of the figure can be shared by all devices. So typically it will be used to localize the different devices in the factory or in the construction site to offer a large-scale user AR experience. And as mentioned also, this map that is updated in real time so that we keep it up to date thanks to all observation done by the different camera on site, will be able to update whether the BIM model or the CAN model. Also, we can imagine to visualize this map or the CAN model updated in VR for improving the design of the factory, for example. And finally, another point is that this very complex CAD model or BIM model with millions of sometimes billions of polygons, we are not able to render them in real time on AR glasses. So we will provide also a service to do some remote rendering. Like that, we'll be able to display very complex 3D model on, I would say, lightweight AR glasses. So this is typically the main idea of the project and the main concept of the project. So to test typically this platform, we have in mind 3 use cases. The first one is a use case that will allow workers to get access to the layout of the factory, to the CAN model, and also to the different data captured by the different IoT sensor positioned in the factory. And what is interesting here is that thanks to AR, you don't need to have a tablet. You have all information that are perfectly registered according to the real world in 3D. And like that, you have access to all the data of the factory directly on the field. And there is no more ambiguity about the matching between what you see on a tablet in 2D and the real environment because everything is well registered in 3D according to the real world. So thanks to that, shop floor personnel can instantly retrieve and view contextual information on the different machines factory. And that's very interesting. On why Air Cloud technology is of real need here, mainly because what we need is to get an access to this kind of information everywhere at any time in the factory. It means that the scale, the augmented reality system have to work at a very large scale, and it have to work the morning, during the night, every time. And for that, that's typically the limitation of current AR technologies, because the map that is used to localize different devices and so to provide some 3D registration are quite limited. And if they are not moved on the cloud, you will not be able to store this huge map of the factories that will provide the localization of the device. So typically here, the test bed, we will conduct a pilot use case in the lead factory for Industry 4.0 of Siemens. The second use case is related to the dynamic production line planning. Typically, the factory is moving. There is some machines that are moving. There is some different elements of the factories that are moving over time. I would say that after 1 week, the CAN model is not up to date and is fully obsolete. So the idea here is to maintain this CAN model of the factory, this layout of the factory up to date like that when you want to plan, for example, an update of a production line, or if you want to do some planification, you are sure that you will be able to simulate the new planification according to the real status of the factory. And I'm not speaking only about IoT, but also the 3D geometry, the position of the different elements of the factory. And of course, that's much better because when you will really apply what is planned, so when you will move the machine in the factory, you are sure that everything will going right because everything has been simulated previously according to a CAD model that have been updated according to the reality. So why again AR cloud technology? Because AR cloud technology will provide a solution to keep up to date this map on so the CAD model of the factory. You don't need to launch some laser scanning of your factory every month. No, you have something that is maintained up to date, and that's very important. And a second point is that on this map that is built by the different AR devices, you will be able to do some machine learning to have a better understanding of your factory based on vision sensor. And you will be able to learn where are the different elements and perhaps much more than that. So again, we will conduct a pilot use case in the Siemens lead factory for Industry 4.0. And the last use case is related to a better construction with AR. So here we can imagine to have a solution for multi-user, so different workers on the construction site. You will also provide some contextual information related to the construction, to the different workers. So the objective, of course, is to minimize the cost and time on a construction site by helping workers and by providing all this contextual information in real time on well positioned according to the reality. For example, one idea is to adjust the forms before pouring the concrete to limit the defect, because when the concrete is poured, it's too late. So if you have to do some update modification, you can imagine to display finally the beam model on your form and check if everything is in place. And if it's not the case, you can also report any effective defects after pouring the concrete, so to build the wall of the building. So again, why AR cloud technology? Because here we are in an environment, construction sites that evolves a lot over time, and every day everything is changing. So you have to keep up to date, typically the map of the construction site that will be used for relocating the augmented reality device. And thanks to that, you will be able to accurately register the reference beam model on the construction site in AR. So concerning the pilot use cases, it will be conducted in FH construction site in Brittany in France. So great, I'm speaking a lot about AR cloud, about mapping, about creating a map of the real environment, but it's not so simple to understand why it is needed. I would like for the people who have not assisted to the webinar on AR Cloud just provide a short reminder. So first of all, when we're speaking about 3D registration is how to register in 3D virtual content. So here typically the 3D model of a robot with the real world, so typically an image marker here behind. That's typically what can provide AR technologies, but how it works really behind, how you can obtain this effect. What you need is to align both the real and virtual viewpoint. So to do that, you have to estimate the viewpoint of here, typically the camera of the smartphone. And you have to align a virtual camera, so the white icon of a camera you can see on the right video, and you have to align a virtual camera with the exact position and orientation as the real one, and with the same calibration parameters. And thanks to that, when you are rendering the virtual robot with the virtual camera and the resulting images, you will put it over the video captured by the real camera, you will obtain the results you have on the left. So for AR devices, AR technology, all AR technology, need to estimate the position orientation of the camera of the device, or I will say if there is several camera of the device itself according to the real world. That is mandatory. And that is the main objective typically of SDK such as the HoloLens SDK, ARKit, ARCore. They all try to estimate the position orientation of the AR device according to the real world to do some 3D registration. And one of the questions is how human is doing. How can you localize yourself in the real world? The main sense used for human to localize himself in the real world is a stereo vision, or at least a vision. So we are using our eyes to estimate our position in the real world. Of course, we have other kind of sense, such as the vestibular that provide you with information about the acceleration of your head. You can use your stereo hearing if you know the sources, sound sources. You can estimate where you are according to these sound sources. Smell, touch, proprioception, of course, is of real need, but proprioception, you do not have something equivalent on AR glasses. On robots, yes, but not on AR glasses. But when I'm speaking about stereo vision, it's not only the vision, it's comparing what you observe with a mental 3D map of the real world. That's typically what is doing human. You visualize your real environment, you will compare it to what you have in mind, the mental 3D map of the real world, and thanks to that, you will be able to estimate your position and orientation according to the real space. Also, when you will move, you will be able to extend this 3D map or to correct this 3D map, for example, if your object have moved. And that's typically what is done by human. And when we have a look to augmented reality glasses, it's quite the same thing. You have, of course, some 4 tracking cameras on HoloLens positioned in front or on the side of the HoloLens that correspond typically to our eyes. And you have also a depth sensor. You have accelerometers corresponding to the vestibular system for human. You have computation capabilities, and you have storage on the device or on the cloud to be able to store a 3D equivalent of a 3D mental map on the cloud. And you have also microphone array corresponding to your hearing system. And you have extra capabilities such as the GPS, magnetometers, or you can also use some ultra wideband positioning system or the kind of technology to position you to position the AR device in the 3D space in the real environment. But most of these solutions are not so accurate, and most of the time we are using the vision to provide an accurate localization of the device, so an accurate 3D registration. So let's have a look to the vision system. And most of the technology are implementing a SLAM for simultaneous localization and mapping. So typically the fact to observe the world, to compare it to the 3D mental map to estimate your position orientation, and when you are moving, the fact to extend this map according to your new observation. Typically, it's the same thing for an augmented reality device. So I will not detail the bootstrap, but first you have to move a little bit your camera to start creating a first 3D map on a very simple 3D map of the real world. And thanks to this 3D map, you will be able to do some what is called tracking. Tracking is, sorry for these images, tracking is just estimating how you move between 2 images. So this one and the bottom right one. And to do that, you will have to extract some key feature in both images and to do some matching between these different features. And when you know how these features are moving between these 2 images, you are able to estimate how the camera has moved between these 2 capture of images. That's typically what is done. So you are able to know that the camera has moved from the orange camera to the blue camera, and so you are able to estimate the position orientation of the camera that have captured the last image. When you have moved enough, you can, after that, do some mapping. Mapping is just a triangulation. you know that 2 points are matching together. Again, sorry for this mistake in the images, but you know that 2 points have moved between 2 images, and these key points are matched together. And so after that, you can do some triangulation and estimate the corresponding 3 points of this feature in the images. And thanks to that, you will be able to extend your 3D map. And what you will do is that you will continue. We'll do some mapping, tracking, mapping, tracking, mapping. And you will be able to both localize your camera and also to build a 3D map of your environment. And what's happened when you come back to a viewpoint that you have already seen, you see that you can have a drift. Because if you have an error during the tracking, of course, this error will be propagated on the mapping. And if you have an error on the mapping, this error will be propagated on the tracking step. And so you have a drift. But you can detect that typically these 3D points here in blue are corresponding to the 3D point, orange 3D point. And you will try to apply an optimization of the full system, including both the 3D point and the camera ear estimation, to optimize the system and to correct it. And here you are able to correct the drift. On this drift correction, when you come back on a viewpoint that has been already observed, is called the loop closure. And here your map is correct. Great. So what you can do, you can store this map, ideally on the cloud. And this 3D map can be used to relocalize new devices that want to connect in a specific environment. So this is typically the 3D mental map used by human, but here it's a digital one. And it is also used for new devices that want to start a new AR application. And when they are capturing the first image, the question is where I am. Where is the AR device according to the real environment? So here we capture an image and we start the application in front of the Eiffel Tower during the night. But the problem is that, again, sorry for this mistake, but the problem is that when you try to match some key points captured during the night with some features that have been built during the day, of course, the matching is not possible. And that's one of the most difficult thing to do, is to provide some relocalization according to a map that has been built in a different kind of environment condition. Different lighting conditions, some objects have moved. When you are comparing the time of observation where you want to start your AR application and the time you have built a map. That's the reason why you have to update this map. Update in real time just to provide good services to other users that want to start AR experience. So when you see some demonstration, most of the time, the mapping is done just before experiencing AR. But for some of you that have seen some demonstration, for example, in different salons, different events, sometimes you have some demonstration where the people say, I am sorry because the lighting condition have changed, so sorry, the AR system does not work anymore. You have to wait perhaps 1 hour to run your system because the lighting condition will come back with a good one corresponding to the lighting condition used during the mapping, and that is not possible for a real deployment in a factory. So that's the reason why AR Cloud is offering interest. So AR Cloud is a persistent 3D digital twin of the real world, continuously updated in real time and offering users shared AR experience. So here is an example. You have a first user with a tablet capturing the experiencing AR application. What he doesn't know is that this tablet will create a map of the real world, a 3D map of the real world. And ideally, if he is connected in 5G, it's much better, and I will explain why just after. Imagine that you have a second user with a second kind of devices, and of course, he will also experience AR with his AR glasses. And of course, a map, a 3D map, will be also built according to the images captured by the different sensors. And if they upload these maps on the cloud, you will be able to do some 3D map fusion. That's very interesting because you will share the same 3D map between the different users. And this 3D map now can be used by other users to localize themselves. And as this user will move into 3D space, they will be able to complete the map, to add new part of the map that have not been previously captured. So they will be able to extend the map, they will be able to correct the map, to remove some parts that are not existing anymore, or to add a new part of the map. So that's really what will happen. And thanks to that, you are keeping up to date a 3D map of your real environment. And you can imagine to do that at factory scale, at a city scale, and why not at a global scale. And you can imagine the value of this kind of data to have a 3D map of the real world at a very large scale, updated in real time. So that's clearly the goal in terms of valuable data. If you want to know more about AR Cloud, there is a webinar organized by the area, but not only, co-organized with XR for All project on Etsy. And you can find it on YouTube. So just have a look to Spatial Computing on AR Cloud, drivers and obstacle, and you will find it. So why I say that these 3D maps are so valuable? Because it's a permanent 3D data stream on the environment and activities of AR user. And when you have this map, and this map is updated in real time, you will be able to launch some machine learning approach to learn a lot of what's happening in the real world. You will be able to detect some object, to recognize some object, for example, in your factory, to estimate the position orientation of the different object, to do some digital twin correction, also to analyze the user activities, the worker activities. So this information is really, really valuable, and that's the reason why there is some confidential issue behind that on a sovereign platform is really crucial for European industry. So if you want to use open source SLAM, I recommend to have a look to the Solar framework. It's open source under Apache v2 license. So of course you can use it also for production. It's cross-platform. Today supported. It supports Linux, Windows, and Android platform. And it's a tool really to create some, I would say, computer vision pipeline, such as what have been presented previously. So a pipeline for tracking, a pipeline for the mapping, a pipeline for the relocalization, for the loop closure. You can create your own pipeline just as if you are playing some Lego. So you have a lot of components available, connect all the Lego blocks together to create your pipeline. The idea is to really to encourage the sharing and integration of innovative AR solutions. What is coming soon is iOS support and also the fact to be able to distribute all this pipeline and to orchestrate them into the cloud. So now let's have a look to the challenges and the proposed solution addressed by this ARtwin project. First of all, as I mentioned, there is some maps that are created by the different AR devices on AR runtime, ARKit, ARCore, HoloLens, and others. The problem is that there are no real specification and no real standard on this map. We have worked on a unique map format in this specification and during this project. And these specifications are provided as an input for the Etsy industry specification group on augmented reality framework for standardization. On one point, one requirement coming from industry is that typically we need to define what are the anchors and to put anchors at the different scale in the factory. So we have defined, for example, a global anchor. So global anchor is specified by a specific localization or location according to the Earth. So just given by your GPS. But from this anchor, we can say that, yes, we want to define a specific children anchor that is positioned at a specific position according, for example, to city of Rennes or München or another. And you want to add another kind of children anchor that is corresponding to a reference coordinate system for the factory. And you can continue and organize hierarchically all your different anchors, for example, an anchor for the cabinet within the factory. And you will attach some different kind of trackable. It could be a fiduciary marker, it could be a point cloud used by and produced by HoloLens or ARKit or ARCore or other. And thanks to that, when the device will detect the map and will be positioned according to the map here, typically it will be able to have its position according to reference coordinate systems that you know in your CAN model. So that's very crucial for industry, because today when you are using ARKit, ARCore on HoloLens, most of all the map are defined in an arbitrary coordinate system. And so you don't know where it is really, and you cannot map the HoloLens coordinate system with a coordinate system of your CAN model, and that's a very big issue. What is defined also is what is called floating anchors for objects that are moving in the factory. Typically, a tool is a floating anchor. It's not really always attached to a specific position in your factory, but you can detect, for example, this driller, and you can imagine to attach some virtual content, but the driller will move in the factory. So that's the reason why we are speaking about floating anchors. And of course, you can attach any kind of trackable fiduciary marker or here a CAD model for tracking this driller. So here it's the organization of the different anchors, and of course, an anchor is a position where you can put a virtual content. That's typically the main objective of an anchor. It's a coordinate system in the real space where you will attach a virtual content. So typically the CAD model of the cabinet or the CAD model or information related to the driller on top of the real driller. So just to imagine an anchor attached to a real element of the real world on which you will attach a virtual content. So concerning the map, or the trackable, but more precisely the map, there is different kind of representation used by AR system. Of course, most of the time when we are speaking about HoloLens, ARKit, ARCore, they are using what is called a sparse point cloud. So here it's just some key points, 3 points of interest that are used to localize the device. And you need also to keep information about the keyframes that are at the origin of this 3D map reconstruction. And you need to keep also the relation between these keyframes, so key images, on the corresponding 3 points, what is called a co-visibility graph, but I will not enter into detail. But you can use points, 3 points, but you can also use other kind of features such as edges. And here you have edge cloud that is much more efficient, for example, for localizing the device according to outdoor environment and mainly according to buildings, because you have very nice line on building, and that's very efficient for localizing a device in the city, for example. But you can also use what is called dense point cloud. And here you see that the number of points is much more higher, and you have much more information about the geometry of the environment. When you have a look to the research, recent research, more and more contribution in the research are related to learned models. So more and more we are not using geometric representation of the real world, but deep neural network to represent finally the world and to allow you to localize your devices according to an image captured by the device. So typically it's not so easy to extract the 3D representation from this learned model, but it's more and more powerful. Typically it's mainly the main and the big players that are submitted on this kind of scientific paper in the conference. So for sure we will have more and more learned model approach in the commercial solution in the next year. One other thing is image retrieval. So typically you have an image capture and you will compare it to images that have been previously captured. You will find the closest one, and if you have the pose of this image, you will be able to estimate the pose of your current images captured in real time. Another point is also the semantic map, because human is also using the semantic of the different objects of the scene to localize themselves. This is something that is coming more and more in research activities. So because we have very nice deep learning approach to do some 2D segmentation in images, and you can move this semantic information to a 3D map when you are doing the triangulation. Thanks to that, you are obtaining a 3D semantic map that is very useful for different purposes. Of course, you need a timestamp. You can provide also some confidence on the different feature, because some feature can be old and perhaps have to be removed or pruned from the different map. And we added different kind of metadata that could be useful. Now I will let Michal present this work. Please, Michal.
Yes. Hello. My name is Michal, and I am PhD student of CTU. So one of the problems or challenges is robust feature matching. So you can see in the papers that state-of-the-art descriptors developed recently can mine a lot of information from local areas in the images. However, the good results are on general images, and there are scenarios where they fail, mainly because the images may be corrupted by over and underexposed regions. You can see on the left side of this video, for example, the corridor, the end of the corridor is overexposed, and entrance doors are underexposed. There is also heavy noise, blur. Usually problem does the repetitive structures and textureless areas, as for example walls where is no structure to localize, which we can use for localization. So, for example, this video sequence was tried to reconstruct by state-of-the-art reconstruction pipelines like capturing reality, Alice Vision, Colmap, and none of them was able to construct one consistent model. So, what's the solution we propose? You can see on the right side some initial results. We propose to calibrate the colors in the images, the exposure time, blur by some pre-trained neural networks, and then highlight some textures in the textureless regions as walls by adaptive median filter. So here on the right side, you can see the denoising and adaptive median filter.
Thank you, Michel. So that's really crucial to improve the matching between two images. So when we are doing some tracking, as mentioned previously, it's not a big challenge, but when you want to match an image capture at a time t and the image capture 3 days or 4 days before, that's become really tricky. And this kind of pre-filtering of images can clearly improve the matching and so all the rest of the pipeline. So typically the quality of the map and the capabilities of a device to localize itself according to the real world. But even if we are applying this pre-filtering, of course, it's quite a big challenge to provide in any way, any time, in any condition, a good pose of the device. So what we plan to do is to use different kind of solution to provide some relocalization. We can use a sparse mapping, so typically what is generally used by AR devices, but we can also imagine to use some dense map to improve the relocalization, because of course here you have not only information about the appearance of the scene, but you have also a lot of information about the geometry of the scene. And so it's much more robust to lighting conditions, for example, that can change over time. Of course, we'll use a commercial tracking system because they are optimized, they are running on specific hardware embedded on design, especially for this kind of devices. For example, on HoloLens, it's called the holographic processing unit. And they are really efficient and powerful, but they have always some drift, and you have to correct it with a good relocalization solution. Or you can use a global navigation system. It's again not so accurate, but it can be used when all other relocalization or tracking solution failed. And thanks to this fusion, we are able to correct the pose and to estimate a pose that is quite good because we will merge all the information coming from different solutions. And what is interesting also is that we can define the coordinate system of reference. So if we say that the coordinate system of reference of the relocalization is based on this specific position on the dense map, you can typically move all the pose of the different device in the specific coordinate system. So you will not only use the coordinate system provided by the HoloLens, but the coordinate system of your choice. So typically a specific position in your factory. And that's of real need. Michel, I'll let you comment on explain this slide.
Yes, so first I will start that it is a very hard task, not solved today, to realize that we know or don't know some three-dimensional object. So to correct some three-dimensional CAD model, which is in the database, we need to recognize that we know or don't know some object. First we need somehow create a three-dimensional point cloud, segmented, and get some three-dimensional object which can be further corrected, which can be further used for correction of some CAD model in the database. There are multi-view approaches which are able to generate really accurate dense point clouds. However, they usually assume static scenes. So one of main challenges for getting three-dimensional point cloud which is related to some objects is filtering of moving objects and removing such a way the artifacts which are caused by this moving parts in the images. So what we want to do is to we propose this loop. We want to semantically segment two-dimensional images at the input to remove parts which are not suitable for localization. Some metallic parts, some moving objects, movable objects in three-dimensional map, etc. By the way, using this semantic segmentation gives us some initialization of three-dimensional map segmentation. Having these images, we can segment CAD models based on two-dimensional initialization of the segmentation. The service for model update can further match segmented objects, mainly use the highly similar objects and update them. Further, there will be also objects which are unknown, so there can be reported for annotation. Having the models, we can render virtual two-dimensional images from artificial poses using some neural rendering approaches to get realistically looking images. And such data can be used at the beginning of this loop to retrain the two-dimensional segmentation of the images and improving the multi-view stereo results. Moreover, synthetic images with known properties can be also used for testing our proposed solution in multi-view stereo, SLAM, and other proposed algorithms. Yeah. Thank you.
Thank you, Michel. So yes, that's very interesting because most of the time when we want to do some deep learning or use deep learning approach, what is missing is the data. On here, this is typically a loop where you can increase the size of the learning data to improve typically the learn model or the train model, here typically for 2D segmentation. So just by generating new viewpoints, and you have already information about the label, that is a semantic information on this 3D map, you are able to extend your model and to improve your model in real time. So that's very interesting. Another point is to scale up, so to do some crowd mapping. So here, I will not enter into detail, but you have different services running all together. The first one is a tracking service, so provided by HoloLens, that will estimate the movement of the device in the real environment. But what we'll be able to do is to create a local map around the device, the HoloLens. It's not done by HoloLens runtime, but controlled by a solution developed during the project. And of course, we'll have a usual pipeline for doing this 3D sparse local map around the device. And here we will be able to detect some change in the, you will capture the different, an up-to-date map of your environment. And you will be able to send this local map to a 3D global map update service that will maintain a global map of the factory. And with this new map, you will be able to correct the current global map. So to maintain a global map up to date of the factory. So for that, you need to do some map overlap detection, some map fusion, and you can imagine that every AR devices will generate a map of their environment, and this map will be used to update a global map of the factory. And from this global map, you will be able to extract some information to do some relocalization and to relocalize the AR device when the user starts the device, or when the tracking failed, or typically when, or just to correct a drift. So this is typically what is down and what will come soon for the 3D global map update service is planned for early next year. Just to show you a video of the local sparse 3D map reconstruction. So here we have a camera put on a drone. It's a public data set. You can see that here it's really challenging because you have a lot of reflective surfaces, and you see that the pose of the camera is quite correct. Here the camera is represented by the white pyramid, and the map is represented by the green 3D point here. The drift is very low, so that was really surprising, and you have a lot of jitter due to the movement of the drone. You have a lot of blur, but the solution developed in this project is quite robust, and you can see that you can create a first 3D map of the environment. Now we are working on merging this map with an existing map just to update the global map of this factory. So let's continue. Here it's another example at a very large scale, the scale of a quarter in a city, and you see that everything is working well also. So we are able to scale, I would say, a full factory without any problem, and use this map to localize the AR device after that. I will let Luis present the remote rendering service. Luis?
Yeah, thank you very much, Jerome. Yeah, hi guys, my name is Luis. I'm one of the co-founders at HoloLight, and within the ARtwin project, we are addressing a big challenge, the question of how to display complex 3D content in real time. And as you can see in the graphics, we have the XR devices, and we have the server side. We have, in this case, on-premise servers, so edge servers. And usually the XR applications are running on the XR devices directly. But in this case, we just have a client application running on the XR device, which is receiving information from the server, and the real XR application is running on the server. And that's a big difference, because one of the bottlenecks is that the XR devices, like a HoloLens or like smartphones or tablets, they have not much performance. So it's not possible to visualize complex 3D models with a high number of polygons. And when we're using more powerful servers, we can really solve this problem. So what's happening is basically that the XR application is running on the server and sending rendered images to the client application. And from the client side, we send sensor data, gesture input, and the SLAM that Jerome just showed you before back to the customer application. And this process is basically happening in real time, so that we get a real-time streaming of rendered images. And the solution, or the thing which is enabling the solution, is our ISAR SDK. The ISAR stands for Interactive Streaming for Augmented Reality. And so it's quite simple. You just integrate the ISAR SDK in an XR application, and then the entire application is streamed. So when we look on the bullet points down, there's really one important thing to mention. We are not just streaming a 3D model, we're streaming the entire AR application. And this is a big difference. And this allows us to work and interact with the 3D content. We get a huge performance boost from the external computer and graphic power. And we have several other advantages. The entire XR application is running on a server side, so there's the data is not stored on the XR device itself. There's just a stream and just images being streamed to the device. So the data is on the servers that companies like Siemens control, and this increases the security. And the last point is that usually you have to develop apps for several XR devices, and it's actually a huge effort to adapt the application to a HoloLens, and then to a Magic Leap next, and then to Android devices. So by having just one application on the server and having different client applications for each device, we simplify the app development process a lot and make it much easier for app developers. And yeah, now I have a video for you where I want to show you that how this actually looks like. Here, our SDK, the ISAR technology, is not integrated in the final solution, but it's in our own application. We have a visualization tool for engineers, and here you can see an engine. This engine has 5 million polygons, so usually it would not be possible to render this 3D model locally on a HoloLens, but in this case it's possible. And as you can see, we have UI, which means that we are able to interact with the model. So it's not just the streaming of a model, it's really the entire application that is rendered, which allows us to interact with the model. And this is a huge difference and a game changer, as it opens up a lot of possibilities, especially when handling point cloud data and all this stuff, which usually would have, nowadays people have to reduce and optimize and simplify this data, but we want to have it in a high quality. And as you can see here, it looks just much better than most applications or most 3D models. And there was basically no effort in bringing this 3D model into AR. And this is our contribution to the ARtwin project. And the next step that we are going to take is to integrate it into the Siemens application and then test it in the factory. So yeah, that's it from my side. I hope you got a good impression, and I'll hand over to Jerome. Thanks.
Thank you, Luis. So let's continue. Yes, I'm sorry. So Another point is that workers have to need a lightweight and low power consumption AR device and to put it on to wear it on the head. So today, existing AR devices are big, are not really lightweight, not so comfortable. So to really have lightweight solution, we can imagine just to have a rig of camera on it and just a display. And what we want to do is to move all computation on the edge or into the edge or distant cloud. We know that, of course, we will need to have a high bandwidth and extra low latency network to be able to meet the requirements of AR technology, because between the time you are moving the head on the image display on the screen of your AR device, and for that you need to do some pose estimation of the device, you need to do some rendering of the scene. The loop have to be less than 20 milliseconds. So for that, you need to have a very extra low latency network, and this is a promise of 5G. So during the project, we will develop this all-in-one case where we will have both the connectivity, the 5G connectivity with 5G RAN and 5G core, but also the edge capabilities with computation capabilities with GPU, CPU, and storage capabilities. And this is a all-in-one solution. So you just put it in your factory, you plug it to get the energy, and everything is working and can be connected to any kind of AR devices. And it will provide all AR cloud functionalities, so localization, rendering to the different devices on the different workers in the factory. And of course, you can connect it to a private cloud, a distant private cloud, when you don't need to have very low latency for specific computations, such as, for example, the merging of the different maps together. So this is typically the one interesting thing. Concerning the architecture, here I will not enter into detail, but you can see all the services connected all together that will be deployed on the cloud. So there is some that will stay and remain on the client side. For example, the image capture and the commercial tracking provided by HoloLens, ARKit, and ARCore will remain on the cloud. But as presented by Michal, the image pre-processing and after the semantic 2D segmentation, the reconstruction of a sparse map or dense map, the relocalization based on the sparse map or dense map, on all you have all the services that have been previously presented during this presentation are typically in this architecture. And here you have the ARtwin map. So here the global map of the factory is stored on this server, on this node. And you see here the remote rendering presented by Luis. Here are typically all the services connected together that will have to be deployed on the cloud. And to deploy these services, we'll use a solution provided by Nokia. It's a platform of platforms, so you're able to build some 5G RAN platform, 5G core platform to connect them to a higher platform that is a telecom platform, and you will be able to connect it to a higher level, the ARtwin service platform, where you will have both the IoT coming from an external platform, the BEAM or PLM service to get access to the different CAN model that is managed by an external platform also, connected them to the telecom platform, and after that connect that to the remote rendering and to the AR cloud providing the pose of the device. So this is typically the vision we have to create platform of platform to be able to manage each platform for provide specific platform from different provider. And to do that, we are connected very low-level components together. For example, if we are speaking about 3D mapping, we'll have a key point detector in images. We'll have, for example, descriptor extraction to extract the descriptor of each key point, doing some matching. So you can connect all these low-level components together to create a resource-facing service. So for computer vision, it will be based on the Solar framework. And after, you can publish this service. You can connect them to other services to provide a customer-facing service. This is typically the higher level of interface where typically we will provide the pose of the device or, for example, the image resulting from the remote rendering to the device. And of course, this device and the application will be used by end user. So just a roadmap, we are developing some services for remote rendering, for mapping, for localization. And the first version will be available in early 2021. The augmented reality edge platforms that have been presented, so the case will be available at the end of the next year. And we'll do the first test in situ at the end of 2021. And after that, we'll have a second version of the services with a lot of improvement, more robust typically, that will be available during the year 2022. And we will test this second version of services during the year 2022. So this concludes my presentation, the presentation of the ARtwin project. Just if you want to know more about this project and to follow it, of course, you have different channels on Facebook, on LinkedIn, on Twitter. Do not hesitate to follow us. And if you want to join the advisory board, just send a mail to this email here, and we'll be happy to count you among the advisory board. Thank you, and sorry to be late. Christine, do we have the time for a few questions?
I think it'd be better not to go longer and to ask people to contact us, yourself or myself, if they have any questions after this webinar. So I'll send an email out with a link to the archive, and that will be the best way to follow up. Thank you, Jerome and colleagues.
Thank you, Christine. I'm sorry to be late.
Thank you very much.
Bye.
Thank you. Bye-bye.